in today's class, we wanted now, you remember that at the end of the last class, we were looking at the effective action for d branes. And we had an action which was Tp divided by, Tp times square root of det g mu nu plus b mu nu plus 2 pi alpha prime f mu nu. This Born-Feld form. You remember that we had some information about Tp. We knew that Tp was equal to T0 divided by 2 pi square root alpha prime to the power p. Okay? Now, so one important question is, can we compute T0? And so complete our determination of this, the effective action for the d branes. That's the question we're going to address today. So in order to do that, what we're going to do is the following. What we're going to do is to look at the cylinder diagram in the presence of two separate d branes. Okay. So suppose we've got one d brane here and another d brane there. And this d brane is, let's say, at 0. This d brane is, let's say, at x. Okay. So let's be a little specific. So let's say that these are Tp branes. So these d branes are parallel to each other, and let's say that they extended in the 0, 1, 2 up to p directions. Therefore, in all the directions p plus 1 up to 25, these branes are localized. So if we draw not the 1 to p 0 to p directions, but the p plus 1 to the 25 minus p directions, okay, then in that space, these d branes are a point. Now the two d branes could be at two different points. Namely, they could be separated by a distance. Like the strings, they could be separated like this. Okay? So let's imagine that they're separated. I mean, it doesn't matter, of course, but for definiteness, let's imagine they're separated in the p plus 1 direction. Or maybe let's say 25 direction. Let's say they're separated in the x25 direction. Okay? So x25 for the first guy is 0. And x25 for the second guy is, let's say, x for this guy. And let's say that the origin of xp plus 1, xp plus 2, xp plus 3, and so on up to x24. Okay. Now what we're going to do is the following. Now what we're going to do is to compute the one loop diagram for open strings that begin at one brane and end at the other brane. Remember now, open strings have Dirichlet boundary conditions. So the endpoint of open strings end on particular branes. Okay? We have to specify which brane each endpoint ends up. So we'll take the beginning point, let's say the beginning point, let's say the open string at 0 to be on the first brane, the open string at pi to be at the second brane. Okay? And what we want to do is to compute this world sheet amplitude. We're computing the cylinder graphs with the boundary conditions that the open string ends, the beginning of the open string ends on the first brane and the end of the open string ends on the second brane. Okay. Now, what are we going to get from this? Well, we're going to do the calculation in 2 minutes. But what are we going to get from this? Most of you remember that, 4 or 5 lectures ago, we did similar computations, but where the open strings didn't end on branes, but were just Neumann open strings. They went all over space. And you remember we found dilaton tadpoles. You remember we did that calculation and we found that we got infinity. And we interpret that as coming from the exchange of massless closed strings. Now, look, suppose you've got a massless field phi. So it's so if we've got a massless field phi, so it's obeying del phi the whole thing squared is equal to, okay, so the action is del phi the whole thing squared. And then you turn on a translationally invariant source for that massless field. As we discussed in the earlier lectures, in the presence of such a source, the equation of motion becomes del square phi is equal to lambda, and there's no translationally invariant solution for this. Phi takes some linear profile, for instance, obey this equation, and you get basically turning on a little bit of a source completely changes the nature of the original vacuum, which was phi equals 0 translationally invariant. Note that that was not the case when you had a mass term. If you had a mass term, you had an m square phi square, then this just changes where the bottom of the minimum of the potential. Okay? So adding a source, a tadpole for a massive field, if it's a small tadpole, barely changes the theory. But adding a tadpole for a massless field was a huge thing. That's why tadpoles were dangerous only for the massless fields, in particular the scalar fields. And it was the dilaton that gave rise to all the trouble. Right? All good, right? Now, that's the case when you've got a tadpole that's translationally invariant. But suppose we've got a tadpole that is smeared over p+1 directions, but it's a point in the remaining 25 minus p directions. Okay? So then what will our equation be? Our equation will be this times delta of let's say of x minus well, let's look for solutions that maintain the translational invariance of the source. Okay? In this case, there were no such solutions. But let's see if we can find such solutions here. Okay? So there were these x directions that went up to p, and the y directions that started at p+1 and went up to 25. So let's say del squared phi of y is equal to delta of y minus y naught, let's say. Oh, maybe it's at the origin in y coordinates, let's say it's the first brain. So delta of y. Now this del squared is a del squared in how many dimensions? In 25 minus p dimensions. Okay? Are there solutions to this equation? Of course there are solutions to this equation. Solutions to this equation are simply that phi, with some number, goes like 1 by r to the power 23 minus p. Right, del square in 3 dimensions goes like 1 by r. Now, this breaks translational invariance, but so what? The original solution broke translational invariance. It preserves all the translational invariance of the original solution by construction. And it's not terrible breaking of translation invariance, because at infinity, as long as 23 minus p is at least 1. Okay? So let's call this D. Oh, let's call this Q. That's the codimension of our space. So this is also 1 over r to the power q minus 2. So if the codimension of the space is 3 or higher, then this perturbation dies off at infinity. Okay? So if you have a dilaton tadpole in the presence of a D brane, which is codimension 3 or higher, that means D25 branes may be trouble. They were trouble, right? Those were the space filling branes that we dealt with 5-6 lectures ago. D24 branes may be trouble, codimension 1. D23 branes may be trouble, but D20, that's codimension 2. You get a log. Okay, but D22 branes and lower will basically behave like point Coulomb sources in the transverse directions. And they will be as little trouble as an electron is in Maxwell theory. Okay? So a dilaton tadpole, which was a very scary thing for a translationally invariant source, okay, just becomes a very routine thing for an object that is localized. Okay, it's as routine as point charges. They source something, so what? That thing, you get the flux that goes all over the place. Is this clear? Okay? So this is what we're going to get. We're going to find do the analog of the dilaton tadpole computation. Okay? And find that when P becomes small enough, there is no divergence anymore. Now that's great. There's no divergence, and in fact, this diagram will compute what? Will compute precisely the interaction energy between these two d branes. Because what it will do is, it's like two charges, right? You've got one charge here, you get this charge sources a potential, and that potential, it's like the interaction energy between two electrons. The exchange of the photon, integrating out the photon, gives you the energy of the two electron system. Okay? So in the same way, what this one loop diagram will do is to compute the energy of a 2D brane system. Is this clear? Okay? Now, what we will then do is to use the fact that we know the form of the effective action. And then if the d branes are taken very far away, then the energy of the 2D brane system should be obtained just by expanding this effective action and integrating out the gravitons and the dilaton. Then by comparing these two computations, we will be able to read off Tp. Is the strategy clear? Okay. So see, one calculation will be just pure string theory. That will give you an answer. We'll take that answer, which is valid at all distances, and look at what happens when the distance between the d branes is very large. Once the distance between the d branes is very large in the closed string sector, only massless closed string should propagate. Now, if we know how the d branes couple to the massless closed strings, and we know how the massless closed strings propagate, we can independently find the interaction energy between these two d branes, like we do in electromagnetism. Okay? But the coupling of d branes to massless closed strings is given by this action. You just take this G and expand it as eta plus H. Okay? And I forgot the e to the power minus 5. That's an important thing. This is the dilaton. Okay? Of course, there's that coupling which is multiplied by this tension, which we don't yet know. So from the effective low energy theory, we will get the answer up to a factor of Tp square. But then by comparing with the string theory answer, which has no unknown factors, we will be able to determine Tp. Is this clear? Okay, good. So we're going to do this calculation, but just one caution before we proceed. One, some of you might be thinking, look, this is unnecessarily complicated. Because really what we should be doing, instead of computing some interaction energy, it's just, well, if there's a single brane, as we've just said, there's some profile of every massless field, some Coulomb profile. So why don't we do this computation? Take the disk and compute the 1-point function of a closed string operator. That should allow us to read off the profile of closed strings. From there, we directly get the tension instead of doing this sort of complicated thing. The thing about this is the following. You see, in string theory, we are supposed to compute, it's very important that we're always computing unnormalized correlation functions. That is, in string theory, we're not computing path integral with operators divided by path integrals with 1. we're always computing path integral with operators by themselves. And it's always very tricky to get an absolute number out of such a thing. Okay? So in a situation where it's much easier to do a calculation where you have some other physical principle that lets you set the absolute normalization. Now, what is good about this computation? What's good about this computation is that in this channel, it's a trace. And that trace then we can compute with normalization because we've got the Hilbert space picture. In fact, if you remember, that's how we did the computations. So for this thing, without any, without trying to be very extremely clever, regulate by zeta functions, all these things, I mean, you can do these things, but you have to be very careful you're not fooling yourself. When you want the answer for a path integral, not the answer for a path integral divided by the same path integral with a different insertion. It's the kind of thing we rarely do in quantum field theory. Right? Try to get a normalized answer for that path integral. Okay? You have to do that very carefully. This can be done, has been done. But it's a more subtle thing to do than to simply work with the 2D branes, where the normalization is completely fixed from the other channel. If you thought of it like this, you'd have the same problem. But think of it this way. Now, the world sheet thing is simply a trace. And traces we know how to normalize. The trace over the Hilbert space, such that each state contributes integer, 1. Okay? So that principle helps us to compute this number with absolute confidence and helps us get the de-Bruijn tension right. That's why this is the calculation we're doing rather than the 1-point function, which of course would be an easier calculation to do. There are other subtleties with the 1-point function, but all those can be dealt with. This is the main issue. Okay? This is the computation that Polchinski first did in 1990, whenever, 95, something like that. And he got very important answers. The answer in the case of the bosonic string is not going to be particularly interesting, some number. But the answer in the case of the superstring turns out to be very interesting. Turns out to be very interesting because you see these d-branes turn out to be charged. The next few lectures we'll discuss all of that. And these charged objects in a supersymmetric theory have a minimum possible tension given by what's called the BPS bound. And what Polchinski discovered was that these d-branes saturated the BPS bound so that they were supersymmetric. Okay? That was a very important thing. First he discovered they were charged. That was not obvious. And then he discovered that they saturated the BPS bound. And hence could be identified with solutions in gravity that people had previously found using gravity techniques. And this was somehow very important in the development of string theory.
So in general, is a saturation of BPS bound is sufficient to imply supersymmetry?
Sufficient to imply supersymmetry. Because the saturation comes from some Q dagger kind of thing.
Oh, I see, okay.
So
supersymmetric curve.
So exactly. So you can something is 0 if and only if it's annihilated by Q. It's like a norm statement. Yeah. Of course, now once you do that, you can directly argue that the things are supersymmetric by looking at the supercharge, how it acts at them. All that we will do. Okay? But that's not how it was done historically. Also, those are subtle arguments. It would be harder to believe until you clear it up completely. There was a great deal of confusion in the 1990s. This is very unsubtle. It's very physical. Okay? So this computation was a classic computation that sort of changed the field. Let me just say 1 or 2 words about that. There were these supergravity solutions. For instance, a solution for the charge that sourced D3 brane flux. A solution that went to area S5 times S5 when you went near the solution. These had been there forever. 1980s well-known solutions.
This area S5 times S5?
Well-known solution of supergravity. Okay? And there are famous, I remember Polchinski giving a talk after the discovery of all the connections, saying that, string theorists were totally uninterested in these things. They stopped and said, and they were right to be totally uninterested. Okay, I mean, they were just some objects. But now, we've got a different description. Now, what Polchinski did was to identify this object with a different description. Namely, endpoints of open strings. Now, once you've got an endpoint of open strings, we know that at low energies, it has a Yang-Mills theory living on it. So this identification is very close to the statement of ADS-CFT. The two different descriptions for the same object. One as a gauge theory, and one as gravity in ADS5 process 5. You have to say, to make that identification complete, you have to take one more step, namely take the decoupling limit. But you're already very close to that. Okay? So this identification of a certain gravity solution with actually being what happens when you take a collection of a very large number of D branes and put them together was basically the statement of ADS-CFT. And it says sort of a lot about string theorists that it took 3 years from this clear understanding of gravity and gauge theory connection to get to ADS-CFT. Why did it take that long? Why didn't Polchinski immediately say, therefore? Just the answer. Actually, it's because the statement seems so absurd. When you first make it, it sounds ridiculous, right? 10-dimensional gravity theories or 4-dimensional gauge theory sounds absurd. How can it be? I think that is what hurt people. And this was Maldasena's greatness, that he took this absurd statement and said, no, but it must be true. Let's believe it and see where it goes. Okay, but again, I want to say that this identification was very near already in my mind to ADS-CFT. Very near. After that, it was inevitable, I think. Okay. Not that it was a not a non-trivial accomplishment to make the edit. Of course it was, but it would have happened. Okay. So what we're doing the bosonic version of what was perhaps one. If you had to name one simple key calculation in the 1990s that changed the field, I would choose this one. Okay. Okay. So let's do this. Okay. So to do the calculation, all we have to do is repeat what we've already done with a few changes. Okay. So where were we? We have this open string. This is 0. This is pi. Okay. And we've got the string stretching like this. I mean, the string is going like that. Now, the only place where the computation that we've already done so far. So let me remind you, what we did was one loop partition function. Okay, we had this from 0 to pi, and then we let this go up to some length t. Okay. Now, or did we call it e to the power t? Maybe we called it e to the power t. Yeah, right, e to the power t, which is sort of like our q. Right, our q was e to the power tau, I tau or something like that. Okay, so let's say that this goes up to some e to the power t. We'll call that q. Q is real for us because we're doing open strings. Okay, now what we have, of course, is simply what we have to compute is trace q to the power whatever, q to the power h, the Hamiltonian of the theory. Now we know that the Hamiltonian of the theory, as far as oscillators are concerned, is the same as just L0 for the doubled theory, keeping only left movers. Okay? And therefore, the oscillator part of this, okay, therefore the oscillator part of this is product n is equal to 1 to infinity, 1 over 1 minus q to the power n. this is true for every dimension. Okay? And then what we had was 26 of these, then we had the ghosts cancelled. The ghosts cancelled 2 of them. So we get this to the power 24. This part has not changed. This you remember? Okay? Now, there's also the zero mode part. Sorry, there's also the zero energy part. The, what's the word for it? The Casimir energy part. The energy of the vacuum part, which again is completely unchanged because it comes from the oscillators. Okay? So we computed it, you know, carefully in the last few classes. I'm just going to look it up from Pulchinski this time. We could go through the calculation again, but what's the point? Okay, and let's see. So we get it's the thing that makes it eta. So eta had a q to the power minus 1 by 24. Somebody remind me. Eta is what appeared with the closed string. So q to the power, I think minus. Yeah, so I think q to the power minus 1 by 24. And then product over n is equal to 1 to infinity, 1 over 1 minus q to the power n. Let's call this eta of q. Okay? And this eta is actually usually regarded as a function of tau. So exactly. So we write q is equal to e to the power 2 pi I tau. Okay. So and here also we'll make it e to the power 2 pi t to match all the conventions. So this will be eta of minus it, so that I can get rid of the I there. Right, so we would get oops, eta of it here. Oh, right, because we want this, and we want trace of e to the power minus 2 pi it. I mean, we want a well-defined partition function. Right? Should be weighted with a minus. So. Is that clear? Sorry for that mess up. We wanted a trace of e to the power minus 2 pi t times L0, so that it's well-defined. You want a negative number here. This makes no sense. Okay, so what we want is eta of it. So that's our definition of eta. Then with that definition of eta, we get the oscillator part of our partition function is 1 over eta of it to the power 24. Okay, this accounted from all the 0-point energy stuff, and accounted for the ghosts, and accounted for all the oscillators. Okay, what it has not accounted for is the zero modes of the X fields. Okay, now let's see what is the situation with the zero modes of the X fields. Okay, what we have is, I think we call that Q, which is equal to 25 minus P. We have Q dimensions which are localized, and P plus 1 dimensions which are not localized. So P plus 1 dimensions are exactly as they were before. For each of them, we have a single quantum mechanical degree of freedom, like we had in all the previous classes. Okay? So each of them is going to give us a factor of integral e to the power minus 2 pi t times p squared by 2m, whatever the effective value of m is for the. For this, we're not keeping track of the alpha prime, so it doesn't matter. Dp. And that will give us, therefore, 1 by square root of t for each of these non-localized dimensions. Is this clear? Shuman, you're not looking happy.
Localized means what?
Localized means Dirichlet boundary conditions.
Okay.
Non-localized means Neumann boundary conditions. Okay? All the directions where the boundary conditions were the same as before, the calculations are the same as before. Is this clear? Okay? So, good. So now let's start putting our, let's try to be a little more systematic. Let's put a line here and we'll write only good stuff here. So we have 1 over eta I t to the power 24. Then we have 1 over square root t to the power p plus 1. And then we've got the zero mode part from the localized directions. So let's take the localized direction. So the two different localized directions. I mean, two qualitatively different ones. The p plus 1th one and the rest. So let's first look at the p plus 1th one.
Why this is p plus 1?
Because there's time, and they're all the p spatial directions. Right? As far as Wilshire theory is concerned, they're the same. Clear?
25 plus 1 and that 1 added up with the p.
Exactly. So p is always the spatial. D3 brings for space-time dimension. Okay. Now, what remains? So now let's look at the p plus 1th guy. The p plus 1th guy obeys the boundary condition that x of 0 is equal to 0. Xp plus 1. I'm not writing it. It's p plus 1. Okay, so xp plus. It's too cumbersome to write. X of 0 is equal to 0, and x of pi is equal to. We give it a name. X. Now in the zero mode sector, we need to find a solution that obeys these boundary conditions.
Previously it was x25.
What?
25th coordinate, right?
I'm sorry, you're right. Let's make it 25th coordinate. Okay? But the solution in the zero mode sector is basically unique. It is, what is it? It is that x of sigma, it has to solve the equation of motion, has to have no oscillations. It's zero mode. Zero mode means linear in sigma and tau. Here everything's in sigma, so it's linear in sigma, and it has to obey these boundary conditions. Okay? X of sigma at every value of tau, okay, has to be equal to x sigma by pi. Okay? So now let's compute the action, the open string action, which is 1 over 4 pi alpha prime d sigma d tau d sigma d tau del x, the whole thing squared for this object, on this configuration. We plug it in and do the integral, so we get just some d tau business, which we can identify now with the energy. Okay, so what is the energy? The energy is, in first differentiate this, so we get x by pi, then square it, and then multiply by pi, because that's the length of the thing. We get 1 over 4 pi alpha prime times x by pi, the whole thing squared, times pi. This is E naught, the energy associated with this unique open string solution.
Is it d tau also?
That the coefficient of d tau is the energy. Okay. So let's see. So this is x squared by 4 pi squared alpha prime. And therefore, there will be an additional factor of e to the power minus 2 pi t times x squared by 4 pi squared alpha prime. Okay? Or make this 2 pi and get rid of this 2 pi, 2 pi. In all the other localized directions, you'll get 0. So this is the full answer. Integral, you remember the measure was dt by t. Integral dt by t, 1 over square root t to the power p plus 1, eta it to the power 24 times e to the power minus t x squared by 2 pi alpha prime. Now let's check with Polchinski and see if we've got it right. Ah. Oh, yes. Okay, looks good. Looks good. 1 over p plus 1 by 2 and so on. Now, Polchinski is also keeping track of all the normalization factors. Okay? All the normalization factors carefully, which we could easily keep track of, right? Because we're just computing a trace, so all the principles are clear. Okay? What have we omitted? We've only omitted one set of factors. Okay? We've omitted one set of factors essentially coming from when we get the zero mode part, it's not just some square root t, there are other factors of alpha prime and pi and so on. Okay? So let's add in those factors just for fun. Those factors go 8 pi squared alpha prime. So where I had, and is it in the square root, outside the square root? By 2, 8 pi squared alpha. This is just from carefully keeping track of this part. We know the mass, so we can compute this. No big deal, right? I'm not doing it. It's no big deal.
To match with the other side.
When we do that, because we need the number. Right? The whole point is to get the number. In everything previous, we didn't need the number. We kept, if you remember in our previous classes, we sometimes had to keep very careful track of relative factors to check if the tadpole cancelled. But since we were dealing with infinity, we didn't care what the absolute number meant. But now the whole point is to get the number, so we're being very careful. Okay, but that's it. That's our answer. Now this answer is nice, but it wasn't the final form of our answer, if you remember, when we looked at the Dilton tadpole business. The final form of our answer we got after doing a modular transformation. Meaning we just did a mathematical trick now. Let me remind you about the mathematical trick we used. In our minds, we remembered that the single boson partition function, the closed bosonic partition function, had to be modular invariant. We computed on a square torus. Okay, that gives us eta of it 1 by eta of it square. Right? Because you have the left movers and the right movers. And it gave us a factor of square root t from the zero mode. Okay? So, but modular transformation here in terms of t is just t goes to 1 by t. Okay? So this must be equal to square root of 1 by t times eta of I by t. We sometimes said this in terms of tau. That was tau goes to minus 1 by tau. But with these factors of I, there's no minus. Now let's keep to the factors of I because that's what we actually want. Okay? So, This, so what we concluded, for instance, was that this also whole thing square. So we concluded that by taking square root, that eta of it is equal to eta of I by t divided by square root of t. So this is just a factor. You can get it from a closed string, but you know, mathematicians had it 200 years before. This is just a fact of mathematics. So we use that fact of mathematics to help process that computation. Okay? So we write this now as dt by t. So the next thing we do, right, first we'll just write it as square root of 8 pi square alpha prime t times to the power p plus 1 over eta of I by t. Now we want by square root of t, 1 by square root of t to the power, right, to the power 24. All good? Okay? And then the next step in our manipulations, just reminding you of what we did before. The next step in our manipulations was to define 1 by t is equal to s. Okay, so this becomes now, so therefore dt by t squared is equal to ds. So let's write this as t squared times t. Okay, some minus signs which you're not taking track of. Okay, so therefore this becomes ds. Now we have 1 by square root of 8 pi square alpha prime to the power p plus 1, we keep that out. We have ds, then we have s to the power p plus 1 by 2, that's this, plus minus 1, that's from here. Okay, and then we have this square root t to the power 24 upstairs, which becomes square root s to the power minus 24, so s to the power minus 12. Okay, divided by eta of is. And of course there's this e to the power minus t x square by 2 pi alpha prime, that becomes, and rubbing this out, e to the power minus x square by 2 pi alpha prime s. All good? Okay. And so now we add up, that's p by 2, s to the power p by 2, minus 20, minus 20,
5 minus p over.
minus 25 by 2. I hope I've got this right. Let's see. That's integral ds times s to the power p by 2 minus p minus 25 by 2, right?
Yes.
That's good, because when p was 25, if you remember last time we had just ds. So it fits with our old result. By times eta of is times e to the power minus x square over 2 pi alpha prime s. And we have to keep a careful track of our 1 by square root 8 pi squared alpha prime to the power p plus 1. Raised, eta is raised to the power 24. Thank you. Okay. Now look at this. This guy here, let's write this as s to the power 25 minus p by 2. What is 25 minus p? It was the codimension. So as before, let's define 25 minus p is equal to q. Okay, so this is square root of 8 pi squared alpha prime to the power p plus 1 ds divided by s to the power q by 2. Okay, 1 times 1 over eta of is to the power 24 times e to the power minus x squared by 2 pi alpha prime s. Now let's see. Where were we most interested in this? Where in this? What kind of values of s are we most interested in for the computation we wanted to do? We wanted the cylinder to become really long. Exactly. So that meant t was small compared to t was small compared to 1. Okay? So in other words, what we want is s to become big compared to 1. Right? So we're interested in s being very large. Now it's precisely large s that previously gave us trouble, because the integral d. Okay, now of course we have to worry about what this guy goes like. So now let us remember, eta of is eta of is to the power 24 what does it look like? Well, this now is e to the power minus 2 pi t times the spectrum of energies in 24 oscillators. But the ground state energy was minus 1 by 24 for each of them. So the ground state energy for 24 of them was minus 1. Okay, so we're going to get minus 1 plus oscillator number. N stands for oscillator number for, and then sum over all possible values of this oscillator number with the right degeneracies. Do you understand what I'm doing? I'm expanding this eta. I'm doing it by a trick. I'm just expanding that. I'm just expanding this. Just think of it as just expanding this. Take this, put it in, that's the minus 1, and then I expand this. Okay? The total energy number I'm calling in. Fine. So this is minus 1 plus, think of it this way, through expansion. The n equals 1 terms here, there are 24 of them. Okay, so there will be plus, okay, so there will be a term with this minus 1, then there will be another term which is plus e to the power 0 with a factor of 24, then there will be plus e to the power 2 pi t and so on with some factor which you could easily calculate and so on. Okay. And that was the whole point of moving to the s variables, right? Because when q is equal to e to the power minus 2 pi s and s is large, then this q is small. So you can just Taylor expand it. So it's very easy to control this eta. In the s variable, in the regime of interest, it would be very hard to control it in the t variable in the region of interest. That's why this modular transform is really, really cool. Okay. So now this term corresponded to the tachyon, and we're going to forget about it. There will be no counterpart of this term in the superstring, as you've already seen with the non-D brane calculations. Right? This thing has no counterpart. This is the thing that gave us trouble in the bosonic string. This was the actual typo.
All that is S, right?
What?
All that is S.
Thank you. Everything is S. And this minus. Thank you. This guy gives no trouble. This guy and all the others because they're exponentially damped at large S. This guy gives terrible trouble, but it's not going to be there in the superstring. We're just going to ignore it. This will give rise to the contribution due to the exchange in energy of a tachyonic object, which is a crazy thing. Right? You hit the tachyon and it starts rolling and all hell breaks loose. That's the infinity then. Okay? The superstring will not have it, so we just ignore that part. Okay? This is the part we want to focus on. Okay? So the part we want to focus on, now I'm clearing this part. Is 1 by square root of 8 pi squared alpha prime to the power p plus 1 integral ds to the power ds s to the power q by 2 e to the power minus x squared by 2 pi alpha prime s times times 24. Clear? Okay. What is this S being integrated from? It's being integrated from 0 to infinity. Okay? And you might say, but well, look, I mean, we should really trust this at 0. We're doing an integral over S. We've assumed that S is large. Then I'm doing the integral from 0 to infinity. Isn't that illegal? But the point is that this integral does not contribute when S is smaller than x squared. That part of that thing completely cuts off that part of the integral. So, as long as x squared divided by alpha prime is large enough, that is, as long as the branes are well separated in string units, okay, you can go ahead and do this calculation from 0 to infinity. Everywhere where it's not reliable, it's anyway 0. The whole calculation is anyway 0. So the error is very small. Is this clear? Okay? We want to compute only the contribution of this thing. You might say it's a bit unclear thing to do if the branes were very close, and this would be correct. But since they're very far away, this is a fine thing to do. This is basically the point that you cannot compare the energies of 2D branes with some effective field theory with only the graviton exchange, unless they're far separated in string units, because the other modes will also contribute significantly.
The coefficient you will get.
What? Gone.
It will not depend on the x.
No, it will not depend on the
There is
x.
some gamma of q.
Yeah, oh, this coefficient, of course it will depend on the x. No, but the coefficient will not. This answer, hang on. Okay. So now we do the answer, we do the calculation. Well, it's of course very easy, because now we move back to a t type of variable. Okay, let's do that. Let's do s is equal to 1 by t. Looks like we're going around in circles. Okay, so ds is equal to minus dt by d square. The minus will work itself out. So we've got 24 by 8 pi square alpha prime to the power p plus 1 by 2 integral dt, and then t to the power q by 2 minus 2. Right? Times e to the power minus x squared by 2 pi alpha prime t. Okay. Now we just do this integral. Well, first, what about this factor? We get a factor of
2 pi alpha prime over x square to the q by 2 minus 1.
good. We get a factor of x, yeah, right, 2, thank you, 2 pi alpha prime by x square to the power, as you say, q by 2 minus 1, just from scaling, because this whole thing has homogeneity. And then we get a gamma of what is?
Q by 2 minus 1.
Q by 2 minus 1. Is that right? Gamma minus 1. What's the formula? T to the power a plus
A minus 1.
a minus 1 e to the power minus
minus
t is gamma of t.
Gamma of A.
Of a, yes. Okay, excellent. So q by 2 minus 1. And so this now is our final formula.
I'm saying this answer depends on x, right?
This answer depends on x, but it should depend on x.
Yes. Now, since your approximation for this integral
Yes,
dependent on the fact that x is very large,
yes.
now it will get correction if it is.
But you know what we're going to do is to compare with the effective field theory answer
At the same limit.
also when x is very large.
Okay. And you have just one number to determine.
Exactly. Right? So, the first thing we do is, let's examine immediately this x dependence.
You were saying whatever x dependency will come in the lower order, the another answer will have the same x dependency.
Yeah, exactly, exactly. We're not going to compare those even. Those will come from exchange of the massive guys. Okay? In fact, it will be exponential corrections because they're massive. Okay. So now let's look at the x dependence. The x dependence is 1 over x to the power q minus 2. Sounds familiar? That's Coulomb's law. Right? So it's 1 over x to the power q minus 2 times, and then we get gamma of q by 2 minus 1. And now we should put in everything in terms of either q or p. Let's see what Pulchinski does. He writes it all in terms of p. So let's see. First he has gamma of 23 minus p by 2. Is that the same as us? Let's write it out.
Yeah.
Q is
Q plus 1 is.
yeah. So right, 23 minus p by 2. So we get gamma of 23 minus p by 2. Oh, what's the, sorry. Yeah, 23 minus p by 2. Then this x to the power q minus 2, let's leave that. That's the Green's function. Oh, right, let's leave that. Then we want all the factors of alpha prime and 24 and so on, all correct. So of course 24 is 24. And then let's look at all these. This was 1 over 2 pi squared alpha prime 8. Thank you. So we have 1 over 8 pi squared alpha prime to the power p plus 1 by 2. And now we have 2 pi alpha prime to the power 25 minus p by 2 minus 1. So 23 minus. -23 p by 2. Okay. And now I'm going to write down what Polchinski gets. Some horrible thing, right? I'm going to write down what he gets, and you guys just check that you guys. I'm just going to write down exactly the way he has it, and you guys are very good at this. You'll check if it's correct. 2 to the power 12, 4 pi squared alpha prime to the power 11 minus p, pi to the power p minus 23 by 2, gamma of divided by mod x to the power p minus 23. Can you check if this is the same, please? So let's look at the pi's. This is pi to the power 22 minus.
Just another pi outside.
Pi, yeah, it's here, right? 22 minus 2p plus p by 2 minus 23 by 2.
P minus p or p minus 20?
Which one? This one?
The x power. The x power is
X power is 23 minus p. Thank you. Are the pi's working? Can somebody check this? It's a horrible thing, right? This is equal to 23 minus p by 2 plus p plus 1. Minus p minus 1. Okay, so this is minus 3/2 20 p. Okay, that works. Then 22 minus 23 by 2 is what? It's 44 minus 23. 21. So it's minus 21 by 2, and here. No, it's plus 21 by 2. Plus 21 by 2, and that works, right? Okay, so pi's have worked. I haven't checked 2's, but I assume they work. Okay, excellent. Now the reason Polchinski writes it this way is that this gamma times this factor of pi times this power of x is the Green's function in q dimensions. Okay, so if you have del squared at g is equal to delta in q dimensions, then g is equal to this object. The power is obvious, and the numbers you can check. Just the volume of the sphere, basically.
This 24 by what?
What?
The first term 24 by?
24 by 2 to the power 12. Okay. So we can write this whole thing here as 24 divided by 2 to the power 12 times 4 pi squared alpha prime 11 minus p times g q of x. Okay. Now all we have to do is to compare this computation with the low energy effective field theory computation. That we're going to get something proportional to GQ of x is almost clear. In fact, the part from the exchange from the dilitons will be GQ of x times something very, very simple. Okay, but you also have the trace part of the graviton that you have to deal with. Okay, so let me ask you guys to do this. Okay, as an exercise now, use the Born-Feld action and compute the exchange contribution from the dilaton and the part of the graviton that contributes. You know, anything that is tensorial will not contribute, as you will see. It has to be basically scalar kind of stuff. Anyway, so you see how that goes. do that calculation. Of course, Polchinski is given it in his book, but try to do it yourself and then compare with him. Okay? It's a simple thing. It's like the two electrons, except there are more fields. There's the dilaton and there's the graviton. Okay? Then you'll get that answer in terms of tension squared times Green's function times some known number. The known number will involve this 24. Okay? And by doing this computation, you find, and then comparing, you find that wow. Well, you find that the TP is basically this, right? He's given it some weird language. What? Maybe P plus. No, yeah, no. T0 of course has to be a mass. It's P plus 1. Probably. Oh God, he's written in terms of Newton's constant. Okay, this is I'll check this. But this is my memory in terms of the most civilized units. The TP is 1 over 2 pi alpha prime to the power p plus 1. Square root to the power p plus 1. Okay? In particular, note in particular that we already had, you see, we already had this dependence, that the dependence on P was with this 2 pi square root alpha prime here. That already follows from this answer. Because this thing, whatever it is going to be proportional to Tp square. So Tp square will have the P dependence of this quantity. So we will have this to the power minus P, which is 2 pi alpha prime, 2 pi alpha prime, square root to the power P. Okay? So the dependence on P is already clear. All that remains is to get that one T0 number out. Okay? And my memory is this. I'll check it for next class. Okay, but you guys also try. Just do the calculation. And, and I'm sorry, and 1 over G. 1 over G, the open string coupling, the closed string coupling, times square root 2 pi alpha prime P plus 1. Where is that 1 over G going to come from? It's going to come from the fact that we had an e to the power minus phi here. So that is 1 over G times e to the power delta phi, the fluctuations of phi. So that 1 over G will enter here. Okay, just do the calculation. Just do the calculation and check. Okay, this part is now basically straightforward. It's about as straightforward as computing the energy of an electron with a proton. Some souped up version. Okay, so we conclude that these objects, source, let's say gravity, okay, have a tension which we've been able to compute. There are two things about the tension that's important. First, that it's 1 over G, and second, the powers of alpha prime. Now the powers of alpha prime, of course, are just dimensional analysis. The 1 over G is interesting. Why is the 1 over G interesting? The fact is here that it's 1 over G, not 1 over G square. Let us remember that Newton's constant. Okay? Let us remember that Newton's constant, the term that multiplied the space-time effective action for the closed strings was 1 over alpha prime to the power 24 by 2 times g square, because there was an e to the power minus 2 phi. Right? This was because this came from sphere amplitudes. 1 over g square was genus 2. Okay? The energy of a d brane is 1 over g, basically because it comes from a disk amplitude. If we were to compute it from the 1-point function of some closed string operator, we would be looking at a disk amplitude, and that goes like 1 over g, because the genus of a disk, instead of being 2, is 1. Okay? Now, what does it mean? So Newton's constant is like g squared, and then factors of alpha prime. The energy of this quantity, Tp, scales like 1 over g. So, if we ask what is the gravitational potential, some fixed distance that doesn't scale with g, away from the d brane, the gravitational potential phi will be like Newton's constant times tension, and therefore will scale like g. So this is very important. It's very important because the d brane is an object. It carries a tension, and it's a very heavy object in string units. It's 1 over g. But yet it's very light in units of Newton's constant. It's light enough so that its effect on the background, the effect on the rest of string theory, on the space on which the closed strings are propagating, is at leading order in the small g limit negligible.
So the decoupling limit can be taken.
Well, the decoupling limit is a bit different from this.
Yes.
But this implies this, you might have wondered, there are two things here that at first seem contradictory. The first thing is I tell you that the d brane is an object. Okay? If it's an object, it carries energy, it sources, it warps space-time. But the second thing I told you is that in the presence of a d brane, we were allowed to do calculation just in flat space, not in warped space, but by putting boundary conditions on our strings moving in flat space. And you might be thinking, how could this possibly be? If I've got an object in warped space, surely my closed string should be moving in that warped space. How could it possibly be that I'm dealing with closed strings moving in flat space and getting the answer right for the interaction with the d brane? And this is the reason. The reason is that the extent of the warping goes to 0 in the limit g goes to 0. So in perturbation theory, to leading order, space is unwarped. Order by order, of course, there will be warping, but that's taken care of by perturbation theory. But the starting point of perturbation theory is unwarped space, just flat space. Okay? Now this is very interesting. The d brane, as we will see as we go along, is a sort of soliton in string theory, but it's like a half soliton. If you take a field theory soliton in a theory with coupling constant g, or let's say g square, so that 1 by g square sits outside the whole action. The action or the energy of that field theory soliton is 1 by g square. Just because in some classical solution there's 1 by g square sitting outside. Here we've got 1 by g square as the natural coupling of our theory. Let's say we're doing, let's say we're studying type 2 strings where there are no open strings in the absence of d branes. So these d branes are thought of as the solitons of the closed string theory, but their action or their energy is not 1 by g square, but 1 by g. So they are heavy objects compared to the fundamental strings, but light objects compared to any classical solution of string theory. That allows them to have an independent perturbative description in terms of an unmodified string theory and just these modified boundary conditions. Okay? It's an unusual situation and very interesting, and lies at the heart of many interesting things in string theory. Is this clear? Now, just as an appetizer, when we study ADS-CFT, what we are going to do is to study not one brain but n brains. So, if we have n brains, then the tension of the string is n by g. So, the potential created outside will be ng. So, now if we look at the limit, g goes to 0, n goes to infinity, gn fixed. Now space-time will be warped. So, there will be a description of the theory, okay? There will be a description of the theory involving closed strings moving in warped space. That will be the gravity side of the description. That will be the ADS side of the description. And then we will have to try to make some argument that we can nonetheless continue to use, in some limit, the description of the theory in terms of the open strings. And then some decoupling business, and that will give us ADS-CFT. Okay? So, ADS-CFT, crucially, somehow it depends on, or at least if you want a big warped space, it crucially depends on this limit, g goes to 0, n goes to infinity, gn fixed. Because we believe ADS-CFT is true for all g and n. Well, that's another story. At least the initial motivation is in this limit. Okay, fine. Any questions or comments?
We believe ADS-CFT is true for all g and n because of supersymmetry. I mean, if we arithmetically change.
You know, it's, in a way, it's almost, yeah, in some sense, yes. Sorry. Okay. Yeah, in some sense, yes. In some sense, yes. Supersymmetry plays an important role. But you know, because an ADS 5 cross S5 see, we know that the near horizon geometry of a D3 brain is ADS 5 cross S5, strictly speaking only at large Gn, where gravity is correct. Okay? But now you can ask, can you prove that there always exists an ADS 5 times S5 solution of string theory at every value of the coupling? Okay? And because the theory is so symmetric, and in particular so supersymmetric, you can actually prove this. You can actually prove that every correction to the equations of motion that you could possibly write down, okay, effectively vanishes in this ADS 5 times S5 background, apart from denormalizing its radius. So, effectively, yes. We get there when we get there.
Some supersymmetric protection.
Exactly. Exactly. But if this is confusing, forget it. At the moment, we are not taking this funny limit. N is fixed, g goes to 0, then it's clear that our space is unmodified. Okay? And therefore, a description in terms of strings moving around in unmodified space is entirely reasonable description, and that's the D-brain description. Okay? Good. Now, next week, Monday, Tuesday, and Wednesday, I'm out. We'll try to have a class on Thursday when I come back. Now it's time. I wanted to talk about D-brains and unoriented theories. And then I wanted to get serious about getting intuition about the superstring. Okay? So, most of the rest of our classes, such as they are, will now be about the superstring, will be about space-time, supersymmetry, all of that.